Hey guys, today we're going to continue our conversation about ionic bonding with a look at a very special type of ionic compound. And these ionic compounds are called hydrates. And you should be able to guess just by the sound of that name, hydra, that this is something that contains water. And that is in fact what a hydrate is. A hydrate is simply an ionic compound that has gotten water molecules trapped inside its crystal lattice structure. And if you remember what a crystal lattice structure looks like, we'll draw one here in a second. You'll see some spaces where you can imagine there to be some water molecules trapped inside. So if this is our cation, remember cations are smaller than our anions, although that drawing didn't give you much of a size difference there. So here's our crystal lattice structure. You can see that there are some spaces between these ions where water molecules can get trapped inside. And so I'll go ahead and draw in a couple waters. Now these water molecules are not bonded to these ions. They are just in the same vicinity. So there's no like chemical bond that's happening here, but this additional water inside the structure, it adds some mass. So hydrates have added mass compared to the normal ionic compound. And because of the water that's in there, it also changes some of the compound's ability to reflect light. And so it will reflect light differently if there are water molecules trapped inside. So you'll often see some interesting colors in our hydrates that we don't see in our typical solid white ionic compounds. So sometimes we get colors. Sometimes, not all the time. There are some hydrates that are also just boring and plain old white. Okay, so because the water molecules add some mass to this compound, these hydrates will have slightly different names and formulas from their ionic counterparts. So remember how we call ionic compounds salts? When it is a hydrate version of that salt, we call it a hydrated salt when we are referring to the hydrate. And if we were to dry out that salt, if we were to remove all of the water molecules that have been trapped inside that crystal lattice structure, instead of a hydrated salt, we can also call it the anhydrous version of the salt. An meaning without. So there are salts that do have water, hydrated salts, and there are anhydrous salts that do not have water. So to show you guys an example of this, let's write the following formula. Here's my normal ionic formula of a salt, CuSO4. This is copper 2 sulfate. Copper 2 sulfate also has a hydrated version where trapped inside the crystal lattice structure, there are 5 water molecules for every 1 unit of salt. And so to show those water molecules that are trapped inside the crystal lattice structure, we simply use a dot inside the formula and then a coefficient showing how many water molecules there are for every 1 unit of the anhydrous salt. And then we name this compound the same way we would normally name an ionic compound. So we would write the name of this compound as copper. I have to work backwards to figure out my Roman numeral of a 2 for the charge. Ran out of room, sorry. Sulfate. and I forgot the L. Let's just see if I can squish it all into one line for you. Copper 2 sulfate. And then we're going to continue the name to indicate that there is a hydrate there. We're going to put a prefix for 5. The Greek prefix is penta. And then instead of saying water, we say hydrate. So this is how we write the names for these hydrates. We do the normal ionic name, and then we do a prefix and a hydrate. And for the formula, we do the normal ionic formula with our balanced charges, and then we do a dot and a coefficient for the number of waters. Now there's all sorts of different variations of these hydrates. There are hydrates that have 2 water molecules and 7 water molecules. And so you're not going to be expected to memorize what salt forms what hydrate. But if I give you a formula, I would expect you to be able to come up with a name. And if I gave you a name, vice versa, I'd expect you to be able to come up with a formula. Now, something that you might not be super familiar with are the Greek prefixes that we use in both our hydrate naming and good news. These are also going to be the same prefixes that we use in covalent naming. Our Greek prefixes are as follows. Mono for 1. Di. Tri. Tetra. Penta. So that's 1 through 5. Here's number 6. Hexa. Hepta. Octa. Some of these will sound familiar from geometry. Nona. Deca. So we only need to know 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are our prefixes. So if I was writing a rule to describe how we would write formulas for hydrates, I would say do your normal ionic formula. And what do I mean by normal ionic formula? Obviously, I mean balance your charges. Cation first, then anion. And then use a dot and a number or a coefficient to indicate how many waters. So normal ionic formula, balance your charges, and then use a dot with a number, coefficient, to indicate how many waters are in that compound. As far as rules for naming these things, normal ionic name. That means name your cation, use a Roman numeral if you need to, and then name your anion. Remember, element, anion endings change to "-ide." Your polyatomic ions are typically 8s or ites, and sometimes "-ide." So your normal ionic name, then prefix, hydrate, to indicate number of waters. Number of waters. And the prefixes that you're going to use are those Greek prefixes right there. And like I said, there's lots of different hydrates. There's calcium, chloride, dihydrate. This is the salt that you guys put on your driveways in the wintertime to de-ice them. So the formula for this would be CaCl2, balance your charges, dot 2H2O. It's an example of a common hydrate. Another one is magnesium sulfate heptahydrate, commonly known as Epsom salts. Any of you athletes take a bath in Epsom salts to reduce swelling. Your formula would be MgSO4, balance your 2+ and your 2- charges there, dot 7H2O. So there's lots of different hydrates out there. They're just sort of a special breed of ionic compounds. Make sure that you can name them and write their formulas. And I think that's all I've got, you guys. Good job.